Interpreting infrared spectra. Have you got it? This short video quiz assesses your understanding of the fundamental aspects of infrared spectroscopy, particularly with respect to functional groups, and your ability to use IR data to aid in the determination of a molecular structure along with proton and C13 NMR data. The quiz consists of 3 questions. It's meant to be taken after you've studied the material and think you understand it. During the presentation, you'll be asked to pause the video to at least try to solve the problem yourself and only then to continue. It won't be hardly as effective if you jump to the solution immediately. Okay, here we go. Number 1, fill in the blanks or circle the correct words below. Pause the video while you answer this, and I'll help you fill them in. Pause the video while you answer this question, and we'll be back with you in a minute. Okay, here we go. Infrared absorptions involve molecular vibration. This sort of excitation primarily involves bond bending and stretching. The energy of light absorbed depends upon the spacings of the quantum levels, which are largely determined in this case by A, the strength of bonds, and the reduced mass of the atoms of the functional groups involved. Thus, bond stretching involving hydrogen atoms, which have particularly low mass, tends to require relatively high energy. Remember, that's because the mass is on the bottom, and the reduced mass will be very close to the mass of the small particle, because if you have a small, less massive particle and a big particle is more massive and you have a spring between them, it's the little one that moves a lot. It's not the big one. Okay, and that leads to a higher energy absorption close to the left end of the standard IR spectrum in the region 3000 to 4000. IR spectra can be thought of as being split into 2 regions, the functional group region on the left and the fingerprint on the right at lower end. While we cannot generally assign the absorptions in this region between about 500 and 1500 inverse centimeters the way we can on the left side, there are many absorptions in this area, particularly many involving bond bending. They present a unique pattern for individual compounds. As such, this region can be used for identification purposes if we have a reference spectrum that we can compare our spectrum to. Number 2, match the 3 compounds on the left to the 3 IR spectra on the right, based on the presence or absence of functional groups in the compound or spectrum. The x-axis units here are inverse centimeters. Note that an IR spectrum can tell as much about what is not present as what is present. So, for example, the IR spectrum shows that there is no carbonyl group. So, there you go, 3 structures on the left, 3 spectra on the right. See what you can do. Pause the video, and I'll get back to you. Okay, we're back. How'd you do? Figure it out? Well, all right. The big deal here is probably that we have 2 compounds that have OHs and 1 compound that does not. We also have 2 compounds that have carbonyl groups and 1 compound that does not. And those are 2 of the most recognizable absorbances in the infrared spectrum. OHs come in the area of 3500 to 3800, roughly. And we can see of these 3 spectra, 2 of them have absorptions, strong absorptions, in this 3500 to around 3800 region. And 1 has a little tiny, looks like an absorption, but you know what that is? If you look over here, there's absorption at what is that? 17, I'm going to call it 1730. Okay? And if you multiply that by 2, that's 3460. And if you look right here, this absorption is 3460. What that is what we call a harmonic. So we're going from the ground state to the first vibrational level at 1730. But there's another level, a vibration, it's like this. And there's another level that you can go to, the second excited state, and that's the 34. We tend to see a small peak at exactly twice the absorption of a very, very strong peak if we have a very, very strong peak in the spectrum. So that's not really an absorption. It's certainly not an alcohol. It's something to check if you think you see that, to divide that by 2 and see if there's a really big peak and see if that's just what that is. I think here's another one. See this big peak down here, and we've got a little peak over here around 3500 in that other compound. Okay, so anyway, looks like we have 2 alcohols, and what we can do is argue that the diketone must be this central spectrum. And we can confirm that by the fact that it has, in fact, this representative ketone absorption at 1730. Okay, so we've taken care of that one. Now, for the 2 OHs, the big difference is that one has a carbonyl group and one doesn't. Well, the carbonyl group region is in the 1700 to 1800 region. And in fact, look at this. This spectrum on the top does not have a carbonyl group, so that must be that one. And that leaves this one here. Now, I want to say something about the carboxylic acid group. This really surprised me when I saw this spectrum because it's quite rare to see carboxylic acid with such a nice sharp peak. Typically, a carboxylic acid will look something like this, just a really broad peak. But I guess it's possible to have them look like this. All right, see how you do that? Process of elimination, looking for places where there is not an absorption is sometimes the most valuable way of looking at an IR. And notice that a very quick glance at an IR can tell you some information that you could use for any kind of analysis, an NMR analysis or mass spec analysis. Oh, I don't have a ketone. Oh, I think I have a ketone. Oh, I don't think I have an alcohol. That sort of thing. That can really speed up the NMR analysis. And remember, in NMR, it's actually quite hard to see an OH sometimes. Number 3, here's a challenge for you. You have been charged with cleaning out the organic lab, and you find a vial containing a white solid. The NMR instrument is busy, so you decide instead to take a mass spec and an IR of the compound. From the mass spec, you discover that the compound has the formula C8H10NO2. The IR spectrum you get is shown on the right. Searching the National Institutes of Standards and Technology database, you discover 3 possible candidates. Which compound is it? Well, now, it is conceivable that you could do this with just an IR spectrum. Back in the 50s and 60s, some 60, 70 years ago, that's what people had and that's what they did. And I was able to go to the National Institutes of Standard Technology, the NIST data, and I found reference spectra for these 3 compounds. They're old, but they have the data and they present us with some interesting challenges. So on the next slide, we're going to see that. Here you go. Here's your IR spectrum. Here's the 3 compounds. And here are 3 spectra that are referenced at the NIST database, probably from, I don't think there's any dates on these, but my guess is these were probably made in the 1960s or 70s. The red marks indicate places on the spectrum that you should ignore because the way these samples were prepared, they were ground in what's called a mull, a Nujol mull or a mineral oil mull, which is a compound that has just a couple of absorptions in the IR. It's a thick oil, used to be used specifically for infrared spectroscopy because it had only these couple of absorptions, but you have to know that those absorptions aren't really of your compound those absorptions of the Nujal mall. So I've marked those. Don't even look at those. They don't count. In addition, I want to point out that the scales on here are quite different, and spectrometers have different scales. If you look at the top of the first scale, you can see it's kind of like a log scale, and even the scale below it isn't exactly even. It gets closer and closer and closer as you get to the right. And then the ones below it have an even scale on the bottom, but it's not inverse centimeters. It's microns. Those are wavelengths instead of frequency. And I would just say, don't worry. So the challenge here is actually to match the spectra, even though it's not an exact match in terms of spacing of the lines. So it is a good challenge. Take a crack at it, see if you can figure it out, and get back to me. Okay, did you figure it out? Let's see. What can we see here? There are many ways of doing this, but my read of the top spectrum is that it doesn't really match. In our spectrum, we're seeing a sharp peak at 3460 some. That's either an NH or an OH. And we're seeing a fairly large peak here. This little spike, notice that, 3358, that is essentially exactly double of that. So that's our harmonic, that's our called the overtone, and we don't have to worry about that. And then what else do we have? We have this peak at 1698, and if we look on this top spectrum, here's 1500, 1600, 1700. 1698 would be right about here, right? So I think that one's ruled out. We do not have a peak there. We have a peak in that top more like 1580 or something like that, but certainly not at 1698. So I'm going to say we strike the first one. Okay, so N-phenylglycine, we're going to say we're knocking out of the competition. Of the next two, if we look closely at this region here on the left in the NH and OH region, we see two absorptions, and that might suggest that we're seeing an NH and an OH, but there are two H's on the NH, so that is actually not definitive. Looking further, how do we match this 1698? Okay, well that's a little tricky here because of our scale in micron. So instead, let's just take little chunks of this and see if we see a pattern of 4 peaks kind of getting smaller and smaller and smaller. Certainly in this side, we have 4 peaks, possibly there. And here we have 4 peaks, possibly there. So that's not clear that that's going to help us too much. We have a big peak at 1250. Now that's looking more like this one, perhaps. And between these two, we have 2 smaller peaks. See this one and this one. And we do see those over here. It's harder to say that we have anything of that nature in here. In fact, if this is our peak that we're calling 1248, there really is nothing in this second spectrum at that point. Okay, so after this peak, we have a set of sort of medium peaks following that, and then a taller peak here. And this looks kind of like that. And, you know, there's not much up here, is there? Okay, so it's looking good for number 3. We continue on. Now this part in the right, this entire region, 1000 to 600, this whole region, 1000 to 600, is this little region right here on our spectrum. Okay, so that's been very much stretched out in this other machine. But what we can see is that in that region, in the top one, we have two major absorptions. In the bottom, we have something like 1, 2, 3, 4. And in fact, that's pretty much what we see here. We even have this little one, which could be this right here. Okay, so the evidence suggests that in fact this third spectrum, that is the match. You really have to go to that much detail to do these matches. You can't just look at it briefly. You have to go right down the line and try to find every single one. So that spectrum is, in fact, 2-phenoxyacetamide. That's how you do it. It's kind of fun. Remember, it is not possible to solve a structure solely from IR data. NMR and mass spec data are far more informative. Nonetheless, IR data can provide clues as to the presence of functional groups, indicating that the compound is an alcohol, amine, a ketone, an aldehyde, an ester, or acid, among others. Generally, work with IR spectra involves finding key bond stretching absorptions. OH, NH, C double bond O, and CO are particularly notable. Often an IR spectrum tells us as much about what is in a structure as what is not. A quick look at an IR spectrum for a key absorption can rule out a functional group and guide an NMR or MS analysis. I'm doing the NMR, I see I have an O, I'm kind of interested, is it an alcohol, is it an ether? I take a quick look at the IR, I say, oh, there's nothing over there around 3,400, must not be an alcohol. Good, I keep going with my NMR spectra. It looks like I have a double bond. Is it a double bond C comes around 1,500, or is it a C double bond O, which comes around 1,700? Oh, quick look. Aha, I've got a carbonyl group in my molecule. That sort of thing. And there are times when the NMR or mass spec data are not definitive, in which case a direct match with a reference IR spectrum, for example, from the National Institutes of Standard and Technology, NIST database, can decide the issue. Okay, so I hope that helped, and I hope you've got it.